Hey everybody, good to be back. We have an interesting twin prime problem here. Now I'm going to let n be equal to 3 times 5. Okay, and that's the smallest twin prime, 3 and 5. Let's see, 11 and 13 would be the next one, I guess. Maybe 17 and 19, but they're primes that differ by 2. It's speculated, and there's a famous conjecture by Goldbach that says there's an infinite number, but as far as I know, it hasn't been proved. But notice that we get that n plus 1 is equal to 4 squared. Right? Okay. And that's what we're going to try to do in general here. We're going to suppose that n is the product of twin primes, and we're going to show that n plus 1 in this n at the totient of n, or the Euler-Phi function, are both perfect square integers. Okay. Now, we've just showed it for n plus 1, all right, just for this special case, all right. Now, let's take a look at this other circumstance right here, 15. And y'all, this Euler-Totient function is what they call multiplicative, and we can write this. Here's my attempt at a phi. Phi at 5. It's multiplicative as long as the input arguments are relatively prime. You can split the operation here. So now we have a phi at 3. Okay, plus 1. Now, y'all, the Euler-Phi function, won't get into a big dissertation on it, but you could almost define prime numbers if you define this first. It counts the number of integers, positive integers less than 5 that are relatively prime to the input argument. Well, in this case, 5 is a prime number, and there's 4 numbers, namely 1, 2, 3, and 4, that are relatively prime to 5. So this would be 15 times 4. Same thing for 3. There's only 2 numbers that are less than 3, 2 positive integers less than 3 that are relatively prime to 3. That would be 1 and 2. And so this would be 2 right here. We have plus 1. Now let's see what this equals. This is equal to 121, right? You have 60 times 2 is 121, and this is equal to 11 squared. So you see, we sort of believe it here for this special case, okay? Now let's prove it in general, okay? Now, this very first proof is very simple because it only assumes that it doesn't matter that p is prime here. It's just the fact that the 2 integers are separated by 2. Now you can go ahead and expand all this out, but you get p minus 1 squared, okay? You can verify that. You can see it pretty quickly. You would get p squared minus 2p plus 1, which is p minus 1 squared. So you see it checks out easily for n plus 1 without having to appeal to the fact that p is prime, other than it's an odd prime. Or no, that doesn't even make any difference. It's just 2 integers that are separated by 2 always have a product plus 1 equals to a perfect square, okay? Now, let's go down and look at, and again, I'll repeat, we did not appeal to the fact that p was a prime number here. Now, right here, we do have to take that into consideration, okay? So right here, again, we have p times p minus 2. That would be equal to n, right? That would be something in the form of twin primes. P minus 2 and p, if they're both prime numbers, that would be a prime number. Now, notice what we did right here is we decremented each one of these by 1. Phi at p would be p minus 1. Phi at p minus 2 would be p minus 3. Now, I may have written that down backwards there. I'm not sure. But anyway, we're just using the fact that both p minus 2 and p minus 1 are prime. Excuse me, both p and p minus 2 are prime. And so phi at p, and that's by postulation, we're talking about twin primes, right? So phi at p is p minus 1, phi at p minus 2 is p minus 3. Now this part's some tricky algebra, and it's kind of a popular problem on the internet. Show the product of 4 consecutive integers plus 1 is a perfect square. That's all this is. What we did, folks, is we did a rearrangement right here. P squared times p minus 3 gives you this. Now notice that this is in the form of a minus 1 right here. and then A plus 1 right here. You'll see that? It's kind of cool. All right. Or it's, this parenthetical quantity is in the form A minus 1, and this is in the form A plus 1, provided we take A to be this entire, and I'll just for emphasis that this is kind of, hopefully this is not going to end poorly. That's our A, right? And so we have A squared minus 1 squared, right? Isn't that cool? Is equal to this object right up here. And that's really the proof that you see. There's probably 100 versions of this problem out there, you know, on YouTube. Okay, but what do we get right here? We get that this is equal to P squared minus 3P plus 1, quantity squared. And it's QED time. Now, this is supposed to be an if and only if, or I think everything is reversible. I just did it in one direction, but I think this is true in an if and only if logically equivalent sort of thing, okay? So let's put QED and we'll check off right here, check off right here, and write QED. Okay? And again, y'all let me know. I think they're logically equivalent, but I don't, it seemed like everything's reversible here, but I'm not sure. I think moving, we just proved it from left to right, if you want to call it that. I think the right to left proof might be a little deeper, a little more problematic. This is very straightforward right here. Okay? All right.